Well, I'm afraid that my talk will not be as funny as the previous one, and it will deal with supersymmetry and the Higgs boson or whatever it is found at LHC. But first, okay, I would like to say some. Okay, just to start with, this doesn't work, no? That's it? Ah, no, I have to switch this. Wait, this one, okay. Okay, so some sentences about Luis. Just the first thing for me is just it is a great pleasure to be here in occasion of his 60th birthday. Congratulations, Luis. You are very welcome. Especially being the only speaker, I think that along with Guido, you, who was not lucky enough to collaborate with you. In my case, I understand that I was invited to speak because of my friendship with you, Luis, and I'm very honored for that. Thank you very much. I cannot say many things about him, as Luis is, without any doubt, one of the greatest theorists of his generation. I don't think that anybody could doubt about this sentence. It is impossible to make a glossary of his scientific achievements just in one slide. Electroweak symmetry breaking in the MSSM, gauge coupling unification, string phenomenology, and many other things, of course. Since Graham will try to do it at the end of this session, so for me that's enough. Just I will say just congratulations, Luis, and I wish you very many fruitful years in the future. Okay. So that's a little introduction for Luis, smallest one. And this is, I'm going to talk about something which is related to supersymmetry. So this is more or less the outline. A little introduction. I will just present the model. Okay, so you will see, and then I will conclude. And this is work done in collaboration with a former student from here, who is Antonio Delgado, that you know him, and my former student, Germano Nardini, who is postdoc in Bielefeld at this moment. So now, okay, some introduction. Of course, as everybody knows, the Atlas and CMS collaborations, for the moment, they are finding no clear discrepancies between data and the standard model prediction with a Higgs mass around 125 or 126 GeV. That's clear for the moment. That's what the data are telling us. So although the standard, the minimal supersymmetric version of the extension of the standard model solves the hierarchy problem, it is true that it requires some fine-tuning in the electroweak sector to reproduce such a, let's say, a mass in the upper region for the MSSM, which creates, let's say, some little hierarchy problem from the heaviest top sector. Okay, that's true. So some non-minimal supersymmetric scenarios are generally motivated to circumvent this little hierarchy problem. So the solution that people have been thinking consists in providing, let's say, some extra tree-level contribution to the Higgs mass. And this can be done in two ways, essentially, either by extending the gauge interactions and adding a D term to the tree-level Higgs mass, or extending the scalar sector by singlets or triplets, let's say. And that's really, to my understanding, the only possibilities. So for instance, extension with triplets and have also extra charge fermions, and they can eventually increase the decay rate of the Higgs into photons, and this can be convenient or appropriate if some excess is confirmed by future data that we have to see. So I will consider for simplicity just a theory with a triplet, with zero hypercharge, the simplest thing. Okay, that's the introduction. Now the model. The model is just very simple. is just adding to the MSSM just this guy here. It is a triplet. This is the structure of a zero hypercharge triplet. This is a 2x2 matrix. It has a zero component and two charge components, psi1 and psi2. And this is just the most general superpotential that you can write with this guy. No? It's a cubic term here, a quadratic mass term, and the usual mu term in the MSSM. So the only subtlety of this model is that if the triplet, of course, acquires a back expectation value, there is an experimental bound on the rho parameter, or the t parameter if you want, which is telling us that this psi0 should be not larger than a few GeV. So then this imposes some constraints. So unless of fine-tuning, of course, this imposes a hierarchy who is telling us that the mass of the scalar, the soft-breaking mass of this extra guy here, should be, let's say, heavier than the electroweak scale in the TeV range, let's say. So in this, once you have this, let's say, little hierarchy here, this implies a decoupling between the scalars in the triplet and the scalars in the doublet. So at the end of the day, the potential is just the MSSM potential plus a quartic term, nothing else. So the model is very simple, yes. Now, okay, in this model, apart from the scalars in the triplet, that okay, we are assuming that they are, let's say, heavier than those in the doublet. So you have, as usual, the pseudoscalar and the charge Higgs with masses which are just very similar to the MSSM ones, but they have here an extra term which is proportional to the back-end expectation value of the Higgs doublet. This lambda, remember that this lambda is the only really dimensionless new parameter, lambda. This is this cubic coupling. It's the only, practically the only extra term coupling in the model. So, okay, so then you can proceed as usual. Of course, the mass eigenstates, let's say little h and capital H, and the original states H1 and H2, and they do not coincide because okay, because you have to diagonalize the mass matrix. And there is the relation, they are related by a rotation with an angle, alpha, let's say, which is a function of the other parameters in the theory. So now I want to make some little comment about that, and it is the following. So when you just compute the masses of those two guys, little h and capital H, in particular the little h, so you are assuming that the mass of this guy is what they are finding at LHC, let's say 126, and you will find that the equation for this computing this mass is provided by some general equation where there is a coefficient which depends, of course, on tangent beta, lambda, and the Higgs mass, which is quadratic in the mass of the pseudoscalar, and then an independent term, let's say equal to 0. So that's one way or the other you will write this equation. And of course, this will fixes the Higgs mass. Of course, if you solve this equation, you can really eliminate one parameter, for instance, lambda, and then you can write beta as a function of lambda just from this equation. And this is what is done here. So this is in the plane tangent beta lambda, this equation for different values of MA, standing from 130, 35, 200, and then let's say very large, which is the so-called decoupling limit, let's say 1 or 2 TeV for MA. This one is the decoupling limit, and then decreasing values of MA are those ones. So there is something funny here, is that all the curves, they just coincide at the particular point here, which is just a particular value of tangent beta, a particular value of lambda. Of course, it depends also on the other parameters, supersymmetric parameters that we have fixed, no? But once you have fixed the other parameters, all of them just crossed at a single point. That's interesting because of the following, because this point is also crossed by the decoupling curve here. And so it shares all the properties of the decoupling limit, even if the mass of the pseudoscalar is as low as, let's say, 130 or whatever.
Doesn't lambda become strong before the unification scale?
Of course, yes, of course. For this value, lambda becomes as strong as 10 to the 8 GeV, 10 to the 10, so something like that. So what we conclude is that for any value of MA, there is a standard model-like point. This is what we call a standard model-like point. And the explanation is that this equation here is equal to 0, but you can really make both coefficients equal to 0, and then there are two parameters, so there is a relation between those parameters. And at this point, let's say the decoupling limit is where MA goes to infinity. So then you just take A equal to 0 in the decoupling limit. So the mass of the light Higgs is the same as in the decoupling limit in this point, this particular point. So that's interesting. So this is a plot of the angle, mixing angle between the Higgses, sine of alpha, along this function beta of lambda, no, that I have presented in the previous slide. And of course, as expected, all the lines cross as the same point for the same value of lambda and a particular value of alpha. And this value of alpha is related to beta by this relation, which is precisely the relation of the decoupling limit. In the decoupling limit, this relation holds. Now, okay, this is now let's say the Higgs coupling are completely determined by this alpha, as everybody knows. So in principle, you can write this ratio of the coupling between the Higgses and the, let's say, different particles, either fermions or gauge bosons, with respect to the standard model value. I call it little r. And this table is just the values of little r at the tree level, of course. And they are a function of alpha and, of course, of beta. No, this is well known. So what happened is that at the standard model-like point, this crossing point, one reaches the standard model values implied, which are precisely for alpha equals to beta minus pi half. So all those r's are equal to 1 at this point, independently on the value of the pseudoscalar mass. So more explicitly, I plot here R for H, let's say bottom, let's say down. Also following the beta of lambda as a function of lambda, and then again you will see that they cross at 1, all of them for the different values of MA. Those are the different values of MA, but they cross at the same point as before. Something interesting here is that for other values of lambda, okay, if you just go away from this value, those couplings can be either very small or very large. So they are probably ruled out by experiments. But at some point, they can even reach the value of 1 in absolute value, but minus, with a minus sign. This is also another possibility that we will see. So this is for the coupling of H to bottom. The coupling of H to the top looks the same. So that's the standard model-like point, and then some departure. More plots with WW or CC is also equals to 1 at this point. And then, okay, but here you see that the departure is not very important. It's the scale is between 0.9 and 1, so okay. And finally, for gamma gamma, this of course this process is not at the tree level. It is induced by one loop effect, but again, this value is equal for all values of MA. Of course, here is not equal to 1. Here it is equal to something like 1.15 or whatever. And the reason is that there is an extra contribution coming from the charginos in the triplet that can enhance, if the charginos are not very heavy, let's say if they are around the present bounds, they can enhance the value of R gamma gamma. Of course, if you put the charginos to higher values, so this point will go down to 1, of course.
The masses of the charginos are determined by the soft parameters for the Gaussian masses and by the effective mu parameter. But in this case, the effective mu parameter seems to be very low, no?
No, I have put an independent mu parameter here.
So you have a mu parameter beside
Yeah. It was in this equation when I showed the superpotential.
Okay.
I'm not trying to solve the mu problem, of course, because.
Not for the mu problem.
So maybe you can ask with the microphone, because since we are recording this, or you don't want to.
No, but no, okay. Here I am fixing mu. I'm fixing some values of the parameter. In particular, mu2, I think that is 250 GeV. I'm fixing mu to 250 GeV. And there is an independent term in the superpotential, so it's not related to the Wagner expectation value of the triplet. This was your question?
Because the contribution of the triplet is very small.
Yeah, exactly. No, yeah. You cannot solve the mu problem with this framework, no? And the masses of the charginos are fixed by M2, and we are fixing M2 such that the mass of the lightest chargino is 104 GeV. This is what we have done there. Okay, right? So at the end, there is we have fixed a number of things here. Yeah. So okay, okay. Those are just the ratio of the couplings with respect to the standard model couplings. But of course, what they measure at LHC is not precisely that, but they are measuring the strength, the signal strength. So then, but that's more or less obvious because from the values of those little r, hxx, which we have determined in the previous slides, one can compute the predicted signal strength of the decay channel. So capital R is just the cross-section of proton-proton given H times the branching ratio of H given the channel XX with respect to the standard model values, no? And that's very simple, no? Because since it is normalized to the standard model values, you don't really need much to compute that. In particular, you can just check the different production mechanisms, gluon-gluon fusion, and the Higgs production in association with a heavy quark, particularly with the top. They are just given as functions of those little r square. Okay, this just comes trivially from the diagrammatics of the different channels here. So, and on the other hand, the vector boson fusion of the Higgs production in association with vector boson is also the same at this order, and they are also provided by the square of little r normalized with respect to the denominator this, which is sum of branching ratios in the standard model times those little r. So, well, at the end, so it's just the original ingredients are the little r, and then you can compute the signal strengths easily. So this is what we have done. So the plot of here I am showing the plot of let's say little Higgs, so the Higgs with a mass of 126 GeV as a function of lambda, of course, along the lines beta of lambda fixing MH. So here the only free parameter again is lambda as before, and for the different channels, no? So so let me just show you. Here I have thick lines and thin lines because in the function beta of lambda there were two branches. But okay, that's so the only interesting branch is the one corresponding to a larger value of tangent beta, which is not very large. It's around, well, okay, you have seen the slides. And the different channels are these ones, no? No, sorry, excuse me. This bottom is just the orange line here. The tau is the dashed line in blue here. The WW and CC is this dot dashed line here, so you can see. And the photon is just the red line here. So you can see here something interesting, no? You can see here that at the critical, at this standard model-like point, all the production are just equal to the standard model ones, while at this point, the production of the photon is something like 25% stronger than in the standard model. Of course, if you move a little bit out in this region, near the standard model-like point, so then you can produce more or less of one or the other. So at the end, you can really make a fit if you want, no? As a function of lambda of the standard model data. We haven't done this fit because, well, for the moment, we believe that the errors are too large, but this can be easily done. And then if you just increase lambda, what happens, as you remember in the previous slides, is that the value of alpha even goes, alpha is negative. It goes to negative, to 0, and then it even goes to positive values. And when it goes to positive values, the coupling to bottoms flip sign, no? So this is what happens here. At some point, it's 0, and then it will start with a different sign. Of course, here you don't see the sign, no, because those strengths are proportional to the squares of this little r. And then you can find here another point, as I said at the beginning, where you can also more or less describe standard model values with some little differences that, okay, here you can produce more bottoms than taus, some little differences of order 10%. And around this point again, so that you can, maybe you can find some reasonable values. And for the moment, this change of sign in the bottom production is not observable, because the only way of observe it is by interference. But the production of the bottom is very small, so the interference is not large. Only for the top, you can really measure the interference, no, but not for the bottom. So this gives a scenario where this is for MA equals to 140 GeV, so it's really a very low value, and then you can really, so you can really hide supersymmetry because you just find the standard model results. This is for gluon-gluon fusion. Something very similar is for vector boson fusion, so I don't want to comment on that since it is very similar. There are also 2 points where more or less you can reproduce the standard model plus some increase here. And then what is here is that, of course, in that case, the heavy Higgs is light, and it could have been found at LHC. So you have to explain why the heavy Higgs. In this case, the heavy Higgs is also around 140 GeV, more or less, the heavy Higgs. So then, but there is a correlation between the couplings of one Higgs and of the other. So for that reason, you expect that the couplings are small for this heavy Higgs. And then this is just the plot for the, in that case, for the gluon-gluon fusion channel for the heavy Higgs into the different channels. So you can see that the rates are completely negligible here. And only, this standard model-like point is here, around here. You can find 10% production of bottoms and taus with respect to the standard model values that I don't think that they could really measure those things at this moment. So this is, for the time being, this heavy Higgs is invisible, but in the future it can be detected, no? In the future it can be detected. So that's it. Now, conclusion. So just to summarize, in this model we can mimic the signal strength of a standard model Higgs. Some small deviations from a pure standard model Higgs can also be encompassed if necessary, for instance, for photon-photon. As I said, what we get is not a very large enhancement in the photon-photon. It can be between 20 and 40%, but not more than that. But of course, it can be smaller. No, it can be smaller. It's just controlled by the Chargino mass spectrum. As I said, when different channels will be measured with more accuracy, one can make a global fit to all data. You can do it already now, no? But and select regions at different confidence level. Unfortunately, we still have to wait a few years until this happens. So, in the meantime, perhaps Luis will produce the final models based on string theories, of course.
I have already done it several times.
Okay. Sorry. Once again. Okay, thank you.
Questions, comments?
Did you look at the dark matter abundance in this model?
No. But in principle, it should be like the MSSM one, no? Because neutralinos, but we haven't. Okay, we haven't seen that. Yeah.
Maybe you have already said it because I arrived late, sorry. But how do you avoid the recent bounds, which are very stringent from LHC on the MA tangent beta plane? Maybe you have commented, but I arrived late. Well, you know that there are very stringent bounds now.
But those bounds
forbid low MA.
But those bounds are done in the MSSM, no?
Yes, but they are quite
so
general.
Here we are not.
Probably in your model you escape it, but I wonder if you have looked into that
Here
because they are very stringent.
The Higgs mass is just completely decoupled from from MA, let's say, because it is controlled by lambda. So in that case...
but these bounds on MA tangent beta plane are not only based on the light Higgs. They are based in very many channels. And are you aware of that? It's a very recent plot.
We haven't done this analysis
very stringent
for the moment, yeah. But that's
maybe you escape it because
that's
you play with lambda, but they are very,
I think that what people claim is that, for instance, for the mass of the charged Higgs, it should be heavier than, I don't remember, 200 GeV or something.
Right.
But here that's very easy because the charged Higgs has an extra term which is proportional to lambda square V square, and that's normally the case here. But I agree with you that we have to...
The combination of large tangent beta and low MA gives large contributions to many things, not only to charge his physics, but only to also to BS, to mu plus mu minus.
To BS mu there is no problem because here we are considering the trilinear coupling zero because we don't need it here. So we are assuming that this can be generated by some kind of gauge mediation or something like that. So the A coupling, the A sub-breaking term is zero. So from that point of view, I don't think that BS into mu is a problem.
Maybe.
But
right. Okay, thanks.
Any more questions? Okay, only one curiosity. This point where all the lines cross corresponds to the no mixing between H1 and H2. I mean, it's just the diagonalization, and then it's independent of the heavy mass.
Not really. No, it's not. No, it's not the low mixing. No. It's
not
look this.
The diagonal term.
No, but
look. To the diagonal
look
term.
here. This alpha. This what you say is alpha equal to 0. Let's say no low mixing. This alpha is well, sine alpha is minus 0.3. No, so it's not really decoupled. No.